How's everybody doing out there? Well, I hope everybody did a good job working with our normal CDF and our normal distributions. And so we're going to continue that study in chapter 6 with what's called the central limit theorem. So the idea is we noticed that if we had a nice normal curve and we could use normal CDF, then we could always find the probability or the area under the curve for these types of problems. But what happens if we don't happen to have a normal curve? How do we find the area under the curve? Well, it turns out because of the central limit theorem that we can take any set of data and turn it into a normal distribution by following a few steps. So let's talk a little bit about what our central limit theorem looks like here and what requirements we need. So the way our central limit theorem works and what allows us to do this is say we have a large sample size of n equals 50. So technically we'll see later it just has to be greater than 30. If we find the mean of everything in that sample and record the mean, and then what we do is we take a sample again. So what we're going to do is take multiple samples and find the mean of all of these different samples. And if we take the mean of the sample means, it turns out it's actually going to be equal to the population means. And so the only thing that's going to be different is that our standard deviation is going to be smaller because what we're doing is we're trying to narrow up our range in this case. So, and I'll see if I can find, there's some good applets online, so I'll see if I can find some applets that'll demonstrate this for you. So, but in general, this is our central limit theorem. So if our distribution is normal, then we can always use the central limit theorem. Or if it's greater than 30, then we can take and find the means of the sample means, and that's going to give us the same thing as the population mean. So if I notice on this side that mu with the x bar, so this is the mean of all the sample means that we took. And this is our just normal population mean. So those two things are going to be the same. And then for our standard deviation, this is where I said it was going to be a little bit different. So our standard deviation from all these samples is going to equal our population mean, but divided by the square root of the number of people. So our population mean stays exactly the same. So if you think about our normal curve, they're both going to be still in the middle, but since our standard deviation is divided by the square root n, it's going to be narrower. So it's going to be kind of a taller, thinner normal curve compared to the original normal curve that we started with. All right, so how does this affect what we do with the calculator? So the only thing that's going to change is just what's going on the inside. So our mean is still going to be technically the same, but our standard deviation, we're going to divide it by the square root of n. So otherwise, this is exactly like what we did in chapter 5. So no different other than we're going to modify the standard deviation because of using the central limit theorem. All right. So here's a little example. Like, I'm not going to have you guys work through this because it's easier to do in class, but it's a good way of demonstrating what the central limit theorem looks like. So I'm going to see if I can find a little applet that I can share with you that'll do the same thing to allow you to see what the central limit theorem is doing. So in the meantime, let's just go ahead and jump in and do some examples. So the mean age of college students in 2008 was 25 years with a standard deviation of 6.8. A simple random sample of 64 students is drawn. What is the probability that the average age of the students in this sample is greater than 26 years? All right, so in this case, so again, we've got more than 50, so we can use our central limit theorem because n is greater than 30. And so we've got our mu of x is going to be 25. Our normal standard deviation is going to be 6.8, and then our n is 64. So if we put this in the calculator, we're going to get normal CDF. So greater than 26, this is going to be our lower bound. And then some ridiculously big number. And then our mean. But now, when we put in our standard deviation, we want to do our 6.8 divided by the square root of 64. So again, that's going to be the only difference between what we did in chapter 5 and what we're doing in chapter 6. All right, so let me flip over to the calculator real quick so we can take a look at what this looks like. So we go to second vars, normal CDF. So we've got our 26, comma, some ridiculously big number, comma, our mean, comma, our new standard deviation with the central limit theorem in mind. And so it looks like it's a 11 point, about 12% chance that a student's going to be greater than 26 years old. So again, notice how I was able to just write in that square root. So don't type it in the calculator first, just type it in exactly the way we wrote it, because we want to get the most accurate answer that we can get. So in this case, we're going to get about a 12% chance of a student being greater than 26 years old. All right, so for B, we're looking at what age of college students will relate to the top 35% of all students. So again, if I think of this from a normal curve perspective, the top 35 is going to be here, and I'm trying to find that z-score that goes along with it. But remember, with inverse norm, it works its way from 0 up. So I need to do 1 minus 0.35. And so the probability that I need to type in is 0.65. So I'm going to do inverse norm, 0.65, comma my mean, comma my new modified standard deviation because of the central limit theorem. And let me flip over the calculator real quick here. Inverse norm, 0.65, comma 25, comma 6.8 divided by square root 64. So it looks like it's going to give us an age of 25.32 years old, or 33. So an age of 25.3 years old. All right. Is that making sense for everybody? So again, the only thing we're doing in this case is just modifying the standard deviation according to the central limit theorem. Everything else is just like we did in chapter 5. So, all right. So let's take a look at example 2. So if the mean weight of a bull is 1,135 pounds with a standard deviation of 97 pounds, would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So, and I used on here, when we use the word unusual, that refers to a probability of smaller than 0.05. So in this case, our n is greater than 30, so we can definitely use our central limit theorem. So our mean is going to be the 1135. Our standard deviation is going to be the 97. Our n is 100. And we're trying to find something less than 1,100 pounds. So when we set this up, we're going to get normal CDF. And we're going to get some ridiculously small number first. Our 1,100 pounds is going to be our upper bound. And then our mean. And then our modified standard deviation. All right, so let's put this in the calculator and see what we get. So normal CDF, something ridiculously small, 1,100, comma, 1,135, comma, oh, what was our standard deviation? Hold on, I forgot. 97, sorry. 7 divided by square root 100. All right, and you probably encountered this before, so when we see that scientific notation with the little e, that means we want to take that number and move the decimal 4 places to the left. So it's going to be a really, really, really small number. So in this case, if I rewrite 1.54 times 10 to the negative 4, 1.54 times 10 to the negative 4, so this is going to look like, so that's going to be our probability in this case, which is definitely less than 0.05, so this would be unusual. And so you may be asking the question, well, how is that unusual? Like, it's only 35-pound difference between the mean and the actual weight. But remember, what we're doing with this 1100 is we're trying to take the average of that 100 head of cattle, and we're trying to say that if the mean weight is 1,135, what's the probability that the average of 100 head of cattle is going to be 1,100? So it's a lot harder to have 100 head of cattle be 35 pounds off the weight, because if this is really true, and their average weight is really 1,100, then what that means is that claim that 1,135 is the actual mean weight has to be wrong. There's no way that can be true if these 100 head of cattle actually do average out to weigh 1,100. Now, what we did in the last section in chapter 5 is we were trying to find the probability that one cow could be 1,100 with a weight of 1,135. So let's just look at that real quick to see. So let me go back through here and delete this square root of 100. And so notice in that case, there's about a 36% chance that a single cow could weigh 1,100 pounds. So again, that's going to be the big difference between our central limit theorem and not using the central limit theorem. So, because the probability that a single cow weighs 1,100 pounds going to happen a lot. 36% is pretty reasonable. But to have 100 head of cattle average 1,100 pounds, if the mean weight is supposed to be 1,135, is pretty much impossible that's going to occur. All right. Does that look good, everybody, for that one? All right, perfect. So go ahead. I've got some practice problems for you guys to work on. 1, 2, 3, and 4 here. And then when you're done, come back to the next video and we'll talk about how to make sure we use the central limit theorem properly. So good.